Good morning. So, as we begin Unit 4 today, there's something I want you to be thinking about. So, Unit 4 kind of marks a shift in the way that we view and talk about statistics in this class, because up until this point, I have only given you data sets with one variable. So, I may have given you a set of numbers and said find the mean, median, and mode. I could have given you a set of numbers and said make a graph, right? Today, we start to look at data sets that have two variables, and what we're going to be doing is trying to find relationships between those variables and talking about how we can define that relationship and use it to make predictions. Okay, so in today's scenario, we have Barbie, and when Barbie isn't busy making blockbuster movies, she's a real thrill seeker. And if I actually had you in person in class, we would be modeling one of Barbie's favorite activities, which is bungee jumping. However, since I don't have you in person, I have recorded some data below. And so what I have recorded is the number of rubber bands that are attached to Barbie as she does some different bungee jumps, right? And so if you look at our two variables, one of them is the number of rubber bands that are attached to Barbie. That makes up her bungee cord. The other variable is her distance traveled, and that is going to be measured in centimeters. So it's important that we understand which variable is explanatory and which one is response. So in this case, our number of rubber bands is our explanatory variable because that's what is used to predict our outcome. And our outcome, or our response variable, is how far she actually travels. So what we're actually saying here is the distance she travels is going to depend on the number of rubber bands. Or another way that I could say that is the number of rubber bands we attach to Barbie will explain how far her bungee jump goes. Okay, so in this case, both of our variables are quantitative, and that's important because if it wasn't quantitative, we would have a difficult time drawing the scatter plot on number 3. Okay, so what's a scatter plot? A scatter plot consists of an x and a y axis, and we graph our explanatory variable on the x, we graph our response variable on the y, and what we're going to do is plot each of the points from this table. So our first point will be 0, 28. Our second point would be the point 1, 34, and so on. Okay? And what you should notice here is that these dots appear to have a relationship, right? They appear to be forming roughly a straight line. And so what that is telling us here is that as the number of rubber bands increases, so does the distance that Barbie travels. And logically that should make sense, right? So the way that we could describe the relationship between these variables is to say, first of all, this relationship is linear. And by linear, I just mean that it's a straight line. It's positive, and I know that because if I read this graph from left to right, it's trending up, right? And the other thing that I can say is this is a strong relationship because if you look at the line that I just drew there, that's kind of my line of best fit. Look how close the dots are falling to that line. So it is a relationship that can be easily predicted. It's a strong relationship. Okay, there's a strong pattern there. All right. So we're going to step back for just a moment to something that we talked about earlier in STA 220, which was correlation versus causation. So here's what I could say. I've been using the word relationship. I could say there is a strong correlation between the number of rubber bands used and the distance that Barbie travels. So notice that I did not use the word causation. Well, we have a variable that we use to stand for correlation, and that variable is called R. Okay, it is something that your calculator will give to you, okay? But if I look at these graphs, let's start with this one right here. So the first thing that I notice is that these dots appear to be trending upward, right? So they have a positive relationship between whatever our variables are, okay? We don't know, the graph doesn't tell us, but if you'll notice here, our R value, or our correlation, is also positive. And that's because the dots are trending upward. The other thing that I want to look at is the value. So R can be anything between -1 and +1. Okay? The closer your R value is to 1, the stronger that correlation is. And I want you to think of it as a percentage, okay? So if you had R equals 1, that is a 100% correlation, which means those dots would be falling in a perfectly straight line. We don't generally see that in the real world. So you're more likely to get something like what you see in number 1. So there's an obvious trend, but those dots are not perfectly in a straight line. My correlation is 0.83. So it's a strong correlation, but not a perfect one. Okay? Then we go to our second graph. And what you may notice is if I were to try to draw a line through these dots are trending down, right? And so that's why our correlation here is negative. Now, again, they're not perfectly in a straight line. Real world data rarely is. And so because of that, our R value is not going to be a perfect -1. It's going to be negative 0.73. So it's not quite as strong of a correlation as we saw in number 1. Okay? Let's see here. Number 3. You can see how those dots are more tightly grouped together, and so we're getting a correlation that is closer to a perfect score of 1, and then it's negative because it's trending down. Graphs number 4 and 6, you'll see the dots are more spread out. One is trending up, one is trending down, but you'll also notice that our R values are lower, right? And that's just because the dots are more spread out. There's not as obvious of a linear pattern. And finally, if you look at this graph here, it's almost like there's no relationship between those variables. Those dots are not obviously trending up or down. They're definitely not in a straight line. And so our R value, or our correlation, is actually very close to 0. There's not much of a relationship there. All right? So on number 2, they're going to ask me some questions. So first of all, do I have a positive or a negative correlation? Well, I have a positive, because if I imagine that I drew a line through these dots, that line would go up, right? What's the strength of that relationship? You could argue moderate or strong. It's definitely not weak because I can tell that they are trending up, and it's definitely not very strong because they're not perfectly in a straight line. But I would say that this one's pretty strong, right? There's a definite trend to this data. All right, so if I were to guess the correlation, and we can kind of compare it to these graphs up here, I would put that correlation around 0.7, just because it looks kind of similar to this graph, right? Except for the fact that it's going up. All right, so the second graph is going to be negative because it's trending down. This one's got a very strong relationship between our variables because look how close those dots are to being in a perfectly straight line. So our correlation is going to be very close to -1. So maybe about negative, if we compare it to this graph, it looks even better than this one, maybe about negative 0.97 or 0.98. So if we were to put those dots in our calculator, we could get an exact answer, and that's something I will show you in a few minutes. But for now, we can get a general idea of what R is. Okay, so here's the thing with calculating correlation. There is a formula, and if you are feeling frisky and you just want to do it by hand, by all means, go for it. I've given you the formula here, and just to kind of explain what's happening, the first thing you do is you calculate the mean from your number of rubber bands, and you calculate the mean from your distance traveled, and that gets plugged in here and here in your formula. Then you would also need to calculate the standard deviation for the number of rubber bands and the standard deviation for the distance traveled, right? And those are things your calculator can do for you. You learned that in the last unit. Once you have that information and you've plugged it in, what you have to do is basically you're getting a z-score from each one of your number of rubber bands. Okay, so you're taking each x value, so you'd start with 0 minus the mean over the standard deviation, and you get that number. Then you do 1 minus the mean divided by the standard deviation, and you'd get that number. And you would do the same thing and get z-scores for your y values, which is the distance traveled. Once you had all of those numbers, you would take all of the z-scores from the x's and all of the z-scores from the y's and multiply them together. So for example, whatever z-score you got for this number and whatever z-score you got from that number would be multiplied together. Same thing here. This z-score and this z-score would get multiplied together. Once you had all of that information, you would add those products together, and finally, you would divide by n minus 1, and n is the amount of data that you have. So in this case, it looks like you have 8 measurements, so you do 8 minus 1, which is 7. That takes a long time. We're not going to ever do that by hand. In the real world, I would never do that by hand. So let me show you how you can do this in your calculator instead. Okay? So if you remember from last time, we can use the stat button to enter in some data, but there's something that I want you to do first. If you click the mode button and scroll down until you see this little line that says stat diagnostics, you need to make sure that that is turned on. Okay, so all I did was scroll over to on and click enter, because if that is not turned on, your calculator will not spit out your R value. Okay, so once that is turned on, then I am going to hit second, which is this blue button, and mode. And what that does is that quits the menu and puts me back to the home screen. So second, mode, and now I'm back to my normal screen. Okay, so just like last time when we had some data, I'm going to click the stat button, and I'm going to press enter. I'm going to choose edit, and I have already entered in the data from that table, but if you need to pause this video if you're working along with me and enter your data, feel free to do that. You'll notice that I skipped the number 5 here, and that's because in just a few minutes they ask us to actually make a prediction based on the patterns that we're seeing of what would happen if we put 5 rubber bands on Barbie. So I left that one out for now. Okay? So once you have your data in, what you're going to do is you're going to click stat again, just like last time, and you're going to go over to calc, again, just like last time, but this time we are doing something different. We are going to scroll down to number 4. LinReg stands for linear regression. Okay, so regression means line of best fit, but what it does is if you think that you have a linear relationship, it will spit out both the line of best fit and any correlation that may be present for you. So I'm going to press enter. The information on your screen should already be correct. It should already have your X value set to L1, your Y value set to L2. So we will scroll down to calculate. And it spits out a lot of information. We will later talk about what all of that means. But for right now, what you need is just the very last number that it gives you right here. Your R value is your correlation, and it tells us that our R value is 0.999. It's almost a perfectly straight line. Okay? So going back to our notes, now we know what R is. R is 0.99. Okay, so the next thing that we can do is once we know R, we can actually start to figure out what our line of best fit would be. And that is something that you will be asked to do by hand in your in your homework, okay? So it's not that you can't use your calculator to help you, but it's not going to just spit out the whole answer. So when we are getting the equation of the line, the first thing we're going to need is a slope. Well, the formula for the slope of the regression line, or the line of best fit, is R times standard deviation of Y over the standard deviation of X. So what our calculator can do, our calculator can find R and our standard deviations for us. Then we can actually do that multiplication ourselves, okay? So we've already got R. I'm going to go back to your calculator to get our standard deviations. So I'm going to go to stat, I'm going to go to calc, and this time I'm not going to go to linear regression. I'm not looking for a correlation. I'm looking for my standard deviations. So I'm going to go to 2 variable stats, and that's just because I have an X and a Y. I have 2 variables. I'm going to press enter, and again, the settings should already be correct. So I go down to calculate, and boom, right up here, and I'll circle these for you. Here is SX sitting right there. So that's my standard deviation for X. And if I scroll down, there's your standard deviation for Y sitting next to where it says SY equals. And so what I'm going to do is I'm going to plug in those numbers into my formula for slope. So slope is equal, once again, to R times SY over SX. Okay? And so if I go back to my home screen, okay, I'm going to start by typing in R. So we got for R 0.999, and then times my standard deviation for Y was 19.152, and then my standard deviation for X was 2.563. And so you'll notice here, I am having to round these decimals, but I want to go out to at least 3 decimal places just to make sure that I can be as accurate as possible. And boom, there is the slope of my line of best fit. So it's 7.465. Okay, so going back to my notes here, we got that our slope was 7.465. Okay, the other thing that I need for a line of best fit is I need a starting point, which we usually refer to as the y-intercept. And again, I have a formula sitting here for you for the y-intercept. So for the y-intercept, we're going to use that slope that we just found, but then we're also going to need the mean of y and the mean of x. So I'm going to go back to my calculator and grab those. Okay, so let's go back to 2 variable stats. Enter, enter, enter. And let's see here, the mean for y looks like is 3.286. Or excuse me, the mean for x is 3.286. And the mean for y is a little over 49. So we're going to plug that information into our equation. Okay, so the mean for y was 49.857 minus, this is the slope that we just got a minute ago. If I'm not mistaken, I believe that was 7.465. And then times the mean for x, which is 3.286. Okay? So if you type that into your calculator, and I'm going to quickly do that, you get, let's see here, 49.857 minus 7.465 times 3.286, you get 25.327. Okay? And there it is. All right, so if I was going to write my equation now for the line of best fit, I have everything I need. I have my slope, which was 7.465, and I have my y-intercept, which was 25.327. And generally what we do is we put this little hat symbol on top of the y. And what we mean by that is this is a prediction line. So anytime you put a little hat symbol, you're saying, hey, this is a line that came from sample data. I can use it to make predictions about the population at large. Okay? So let's talk about how you could have done this a little bit quicker using the calculator. Again, you will be asked to do both on your homework, so you need to know how to do it by hand, but also how to do it in the calculator. So if I go back to your TI-84, if I go to Stat and over to Calc, if you go to Linear Regression, okay, and you let it spit out that list of numbers for you, it will spit out all this information for you. So A is your slope, B is your y-intercept, and then R right here is your correlation, and we will talk about in just a moment what R squared means. We're not quite there yet, okay? So then what I could do My little y hat equals 7.464x plus 25.333. And so if you notice, when we let the calculator do the work for us, it is very, very similar to what we got by hand. It is just slightly different. There's a difference of like 1/1000th right here. And that is probably just because I did have to round my numbers. Your calculator doesn't have to round, right? So it may be just barely different, but not enough to make a real difference. Okay? So let's go back to your notes. And in case you forget the calculator instructions, I do have these written down for you right here. Okay. So in our next scenario here, we have Tyler, and Tyler wrote a book called Spurious Correlations, in which he investigates relationships between quantitative variables. And that's actually the website that I don't know if you remember, but I showed it to you, I guess it was back in the first unit, where it's just these crazy correlations, like there's a correlation between margarine consumption and the divorce rate, right? So it's all about correlations that happen in the real world, but they don't really make sense. So one such example is the strong correlation between the number of letters in the winning word of the National Spelling Bee and the number of people who died by venomous spider bites in a given year. So here is the data for an 11-year span. Okay, so what do I notice? Just by looking at this graph, so letters in a winning word is going to be my explanatory variable. I know this because it's located on the x-axis on the graph. Deaths by spider bites is going to be my response variable. Okay, and I can tell that my correlation between these two is going to be positive, right? Because these dots are trending up. And when I look at the correlation value is 0.806, which is strong, right? There is an obvious positive linear trend here. Okay? Part B asks me to calculate something called the coefficient of determination, or R squared. So the way that I calculate this is by taking the R value that they give me, which is 0.806, and actually squaring that. So if I go over to your calculator, and I do 0.806 squared, that is, we'll call it 0.650. Okay? So my R squared value is 0.650. Well, what does that mean? So R squared is actually the percent of variation in your response variable that can be explained by the variation in your explanatory variable. Okay? So what I could say is 65% of the variation in the number of deaths can be explained by the variation in the number of letters in the winning word. So why is that important? So here's the thing. If 65% of the variation in this variable can be explained by this variable, that means 35% of the variations that we're seeing must be explained by something else. There are some other factors at play here, right? And that kind of makes sense because we don't really expect letters in the spelling bee to have much to do with deaths by venomous spider bite. Okay? So part C, there is a strong correlation between these two variables. Does this mean that the longer winning words in the National Spelling Bee caused an increase in the number of deaths by venomous spider bites? No, it doesn't. For whatever reason, there's a correlation. Maybe there's some kind of weird confounding or lurking variable that we haven't even thought about that's causing the relationship between these two. But we can't just assume because there's a correlation between two things that one has caused the other. Okay, and the last thing we're going to talk about is how can we use the information in this chapter to make predictions. So I have already written out for you, once again, our line of best fit that we got from our Barbie Bungee data. How could I use this to make prediction? Okay, so if I know that equation, think about what X and Y stand for. X stands for the number of rubber bands. Y stands for the distance traveled. So number 2 asked me to predict the distance that Barbie would travel if 5 rubber bands were used. So what I did is I just replaced the letter X with 5. I typed it straight into my calculator, and that gives me a prediction of 62.653 centimeters traveled for 5 rubber bands. Okay? So then on question number 3, let's say that later on you actually decide, hey, I want to use 5 rubber bands, actually do this experiment, have Barbie bungee jump off the side of a table, and see how far she goes. And then you realize that she actually traveled 64 centimeters. Okay? So if you compare your prediction to your actual data, were they exactly the same? No. Right? And we don't expect that with real world data. There's always some variation. Okay? But it should be close. So our prediction was only off by about 1.3 centimeters. And that error in there between our prediction and what actually happened is called our residual. Okay? Now, question number 4 is something that is very, very important. If you don't learn anything else from this class, this is what I want you to understand. So in number 4, it says predict the distance that Barbie would travel if the group used 20 rubber bands. So if I plug 20 back into my equation from number 1, I get a prediction that Barbie's going to travel 174.613 centimeters. The question is, can you trust this prediction? And the answer is absolutely not. This is called extrapolation. So if you look at the data that we had, we only did testing up to 7 rubber bands. And that's how we got our equation that we're using to make our predictions, right? Well, if I only did testing up to 7 rubber bands, I can't assume that that equation is going to be accurate when I plug in the number 20, right? Because I haven't tested it, okay? This is exactly what happened when COVID occurred, right? So we would turn on the news and we would see all these graphs, and they were predicting that there were going to be millions of deaths, and not that COVID wasn't bad, it was terrible, but these graphs were blown way out of proportion because the scientists were taking, these small amounts of information that they had from the first few weeks of COVID, and they were using it to extrapolate for how many numbers of deaths and illnesses there would be months and months later. And you just can't do that because over time, patterns change. You can't assume that the pattern that you see at the beginning of a disease or at the beginning of a bungee jump or whatever the case may be is going to be the same pattern that you see, months and months later. Okay? So extrapolation is very, very dangerous because it causes inaccuracies in our data. You also see this in the weather forecast. So if you look at the weather forecast in January, 3 weeks before they're calling for snow, it'll tell you that there's going to be 2 feet of snow. What actually happens 3 weeks later, by the time those weather patterns get here, we don't get any snow, right? So extrapolation has to be taken with a grain of salt. If you are going to extrapolate, you have to kind of understand that your predictions may not be accurate. Okay? So the last couple things I want to talk about. So question number 5, what is the y-intercept of our regression line? So the y-intercept is sitting right here. It's kind of the idea of our starting point. Where is Barbie, or how high is she before she has, or excuse me, how far would she travel if I just dropped her with no rubber bands, right? So here's the thing about the y-intercept. If you interpret that and you say, if the bungee cord had 0 rubber bands, the predicted distance traveled is 25, right? That doesn't make any sense. So when you make a line of best fit, your y-intercept is going to be the point that best fits a straight line. Well, in the real world, we know that if we don't put a bungee line on Barbie, she's not going to travel anywhere at all because she's not going to jump, right? So take your y-intercept with a grain of salt. That point is there to create a straight line. It may not actually fit a real world scenario. However, your slope should. So your slope of 7.464 is telling us that every time we add 1 rubber band to that bungee cord, we predict that Barbie's distance traveled will increase by about 7.464 centimeters. That is something that you can apply to your prediction, and that should make sense in a real world context. Okay? All right, so that is the end of our Unit 4 notes. Have a great day.